Hello everyone, my name is Antonio Agresta. I'm a PhD and a researcher at ENEA, the Italian National Agency for New Technologies and Energy and Sustainable Economic Development. More specifically, I work in the laboratory for hydrogen research and basically all the technologies related to hydrogen. In this lecture, I will talk about metal hydrides as a safe hydrogen chemical storage, and I will give a brief overview of such a complex and wide argument. The motivation of talking about metal hydrides is mainly due to the critical importance that is assuming hydrogen storage as a key enabling technology. Since hydrogen is poised to play a transformative role in various applications, including, for instance, stationary power, portable power, and transportation, with the highest energy content per mass of any other fuel, hydrogen presents significant advantages, of course. However, it has a very low density at ambient temperature, and this results in a corresponding low energy per unit volume. This challenge underscores the necessity for innovative storage solutions that can achieve higher energy density. In general, hydrogen can be stored in several forms: physically, as either a gas or a liquid, and gas storage typically requires high pressure tanks operating at pressures between 350 and 700 bar. That's to say 5,000 to 10,000 psi. Alternatively, when stored as a liquid, hydrogen must be maintained at cryogenic temperatures, given its boiling point of minus 252.8 degrees Celsius at 1 atmosphere of pressure. This, of course, requires a great deal of energy. Furthermore, hydrogen can be stored through adsorption on solid surfaces or absorbed within solid materials, which each method offering distinct advantages and challenges. As we progress through this presentation, we will delve deeper into these topics, mainly the topics implicating the adsorbing and absorbing process. In the next slide, we see a schematic and an overview of the various hydrogen storage methods organized into two main categories: physical-based and material-based storage. The accompanying diagram basically illustrates these methods, highlighting their distinct characteristics and applications. For the physical-based storage methods, we can find compressed gas storage, and this method involves basically storing hydrogen gas at high pressures in specialized tanks. While it allows for efficient storage, it necessitates robust materials to manage the high pressure, and volumetric energy density can be a limiting factor. The other physical-based storage method is the cryo-compressed storage. This is an innovative approach combines aspects of both cryogenic and compressed gas storage, involving the storage of hydrogen at both elevated pressure and low temperatures. This method can enhance storage density while reducing the risks associated with high pressure gas storage. Finally, under this category, there's the liquid hydrogen storage. In this approach, hydrogen is stored as cryogenic liquid at very low temperatures. This method offers a high volumetric energy density compared to gaseous storage. However, it requires substantial energy for liquefaction and poses challenges related to insulation and handling. Shifting to the material-based storage methods, we have, of course, the main topic of this lecture, the metal hydrides, and we will go into these later on. Then we have the chemical hydrides, similar to metal, Here, chemical hydrates store hydrogen in chemical compounds. While they can achieve high storage densities, the release of hydrogen often requires specific conditions, which may limit their practical applications. The adsorption, we can see here adsorbent. The adsorption method, hydrogen molecules adhere to the surface of solid materials, such as activated carbon or metal organic frameworks, the so-called MOFs. This technique can operate at ambient temperatures and pressures, offering potential advantages in safety and efficiency. Then we have the so-called liquid organic hydrogen carriers. This emerging method involves storing hydrogen in liquid organic compounds, which can be reversibly hydrogenated. The so-called LOX offer a promising way to transport and store hydrogen safely at ambient conditions, simplifying logistics. Now we can proceed to the next slide, and we go deeper into the main topic of the lecture. Metal hydrides are of significant interest in the pursuit of efficient and sustainable energy solutions, given their capacity to absorb and release hydrogen gas, as we said. This characteristics positions them as a viable candidate for various applications, including fuel cells and energy storage systems. While metal hydrides typically exhibit good energy density, it is important to highlight here that their specific energy is generally lower than that of conventional hydrocarbons. This aspect presents both challenges and opportunities for ongoing research and development efforts. There is in general a wide range of metal hydride materials, including magnesium hydride, lanthanum nickel hydride, sodium aluminum hydride, each distinguished by unique properties and potential applications. As we progress through the presentation, we will delve deeper into the advantages and limitations of these materials. This is a very simple slide that shows the exothermic nature of hydrogen adsorption, which releases heat, and the endothermic requirement for desorption, which needs heat input. This figure in specific demonstrates how heat influences the absorption and desorption cycles in hydrogen storage materials. This would give a very first glance to grasp the role of thermodynamics in designing more efficient hydrogen storage systems. Okay, let us delve into the fundamental chemical reactions involved in hydrogen storage, specifically focusing on the interaction between hydrogen and metal hydrides. The equation here presented is the general equation that shows how a metal can join chemically to hydrogen. It highlights the reversible nature of hydrogen adsorption and desorption in metal hydrides. The conditions of pressure and temperature play a critical role in influencing this process. By altering these parameters, we can control the extent to which hydrogen is either absorbed into or released from the metal hydride. At low temperatures or high pressures, hydrogen atoms can effectively penetrate the gaps within the parent metal structure, like we saw in the slide before, leading to the formation of a solid solution. This solid solution is integral to the performance of metal hydrides as hydrogen storage materials, allowing for greater storage capacity and efficiency. As we proceed, we will explore the implications of these reactions on the design and optimization of hydrogen storage systems, as well as their relevance in practical applications. As I was saying, the mechanism of actions involved in this type of storage system is to create uh, a, un a unified system that has metal component and hydrogen component. Um, Hydrogen can be effectively stored in solid forms, and its release from these solids can be influenced by variations in pressure and temperature, as well as through specific chemical reactions. This dual approach provides flexibility in managing hydrogen storage systems. The process of hydrogen adsorption in solids is exothermic, meaning that as hydrogen atoms are absorbed, the energy of the system decreases. The excess energy released during this process manifests as heat, which is a critical factor to consider in the design of storage systems. Conversely, the desorption of hydrogen requires the input of heat, which must be adequately managed to ensure efficient hydrogen release. Understanding these thermodynamic principles is essential for optimizing solid hydrogen storage materials, allowing for improved performance in practical applications. As we move forward, we will discuss various solid storage materials and their advantages and limitations. Here, we turn our attention to the thermodynamic behavior of metal hydrides, particularly focusing on the absorption's isothermal lines illustrated in the accompanying diagram. This diagram represents the relationship between pressure, composition, and temperature, effectively capturing the thermodynamics of hydrate formation during the storage and release of hydrogen molecules and atoms within a crystalline structure at constant temperature and varying pressure. In this context, we can identify distinct phases of hydrogen storage. The so-called alpha phase, and this phase corresponds to the fusion of hydrogen atoms within the crystal lattice of the metal hydride. It is characterized by the initial absorption of hydrogen into the structure. Then we shift to the alpha-beta phase. This region indicates a transition at constant pressure known as the P-plateau phase, P-plateau being a constant pressure. It is associated with the formation of hydrates as the lattice begin to fill with hydrogen. Lastly, we have the beta phase. In this phase, the lattice reaches saturation with hydrogen, signifying that it can no longer absorb additional hydrogen atoms. Understanding these phases and their corresponding pressure composition relationships is crucial for optimizing hydrogen storage materials and improving their efficiency in practical applications. We will go on with the mechanism of action of metal hydrides. A crucial equation, again, in the thermodynamic behavior of this material is the so-called Van 't Hoff's law. And it's very relevant to the thermodynamics of the hydrogen storage. Van 't Hoff's law provides a mathematical relationship between the thermodynamic quantities of pressure and temperature in the context of hydrogen absorption and desorption process. This relationship is expressed by the expression you see in the slide. The P plateau here, as I was saying before, refers to the pressure at which hydrate formation occurs, while P0 represents the initial pressure. The quantity delta H and delta S correspond to the changes in enthalpy and entropy, respectively, during the reaction. It is essential to note that there is an activation energy associated with the adsorption process. This represents a minimum energy threshold below which hydrogen adsorption does not occur. Additionally, the process of hydrogen absorption and desorption is inherently irreversible. This irreversibility arises from factors such as the deformation of the crystal lattice and other dissipative effects which contribute to the hysteresis observed in the adsorption-desorption curves on your left. Understanding these thermodynamic principles is critical for the design and optimization, again, of hydrogen storage systems. Next, we have the different category of metal hydrides, which are compounds formed through chemical reactions, as we've seen so far, between metals or metal alloys and hydrogen. These compounds can be classified into three main categories: ionic hydrides, interstitial hydrides, and complex hydrides. Ionic hydrides are characterized by the bonding of hydrogen to alkaline elements from the first or second group to the periodic table. The accompanying table provides an overview of some of the most common ionic hydrides. Among these, we find magnesium hydride. It stands out as particularly noteworthy due to its high volumetric capacity of 109 kg of hydrogen per cubic meter and gravimetric capacity of 7.6 mass percentage. These properties make magnesium hydride an attractive candidate for hydrogen storage applications. However, it is important to note that the temperature required for hydrogen release from magnesium hydrides is relatively high if compared to others, exceeding the 300 degrees Celsius, that's 573 Kelvin, at atmospheric pressure. This factor presents challenges that must be addressed when considering the practical implementation of magnesium hydride in hydrogen storage systems. As we were saying, there are always advantages and disadvantages. So the advantages of using ionic metal hydrides are certainly high stability. Ionic metal hydrides formed from alkali or alkaline earth metals tend to have high chemical stability. The stability makes them safe for storage and handling, reducing the risk of unintended reactions. They also have a simple formation. The synthesis of ionic hydrides is generally straightforward, involving direct reactions between metals and hydrogen. This simplicity can lead to lower production costs and easier scalability. Then we have good hydrogen storage capacity, as I was saying. Some ionic hydrides exhibit competitive hydrogen storage capacity, making them suitable for applications that require efficient storage solutions. And then we have high hydrogen release rates. Ionic hydrides often demonstrate relatively fast kinetics for hydrogen desorption, allowing for rapid hydrogen release when needed. This property is advantageous in applications requiring quick energy retrieval. The established use cases of ionic metal have a long history in various applications, including batteries, chemical hydrogen systems, which provides a wealth of knowledge and experience in their handling and applications. Finally, they have a low environmental impact. Many ionic hydrides consist of abundant non-toxic material, making them environmentally friendly, and they are a good option if compared to some complex or rare materials. Next, we will focus on the interstitial hydrides, which are formed by hydrogen and elements from groups 3 to 5 of the periodic table. In these compounds, we see a very sketchy image on the right. In these compounds, hydrogen atoms are effectively trapped within the host crystal structure of the metal. Among interstitial hydrates, lanthanum nickel hydride, represented by the formula we see here on the right, LaNi5H6, is of particular interest. While it exhibits lower volumetric capacity, and we're talking about 89 kilograms of hydrogen per cubic meter, and gravimetric capacity 1.4 mass percentage, compared to magnesium hydride, the lanthanum nickel hydride has the advantage of absorbing hydrogen at room temperature and atmospheric pressure. This characteristic makes it a valuable material for applications where ease of hydrogen absorption is critical. The advantages, like we did for the ionic compound, are: the first one is the room temperature absorption, as already said. These interstitial hydrates can absorb hydrogen at room temperature and atmospheric pressure. This property, of course, simplifies their integration into practical applications and reduces energy costs associated with heating. The second advantage is the high reversible capacity. Interstitial hydrates typically exhibit good reversibility in hydrogen absorption and desorption, allowing for efficient cycling and reuse. This characteristic is crucial for applications that require repeated hydrogen storage and release. The third advantage is their simple structure. The crystal structure of interstitial hydrates is often simpler compared to complex hydrates that we'll see next. This simplicity can lead to easier processing and synthesis, making them more accessible for various applications. The fourth advantage is the lower cost. Some interstitial hydrates may be composed of more abundant and less expensive material, making them a cost-effective option for hydrogen storage solutions. Then there is the good thermal stability. Since they exhibit good thermal stability, which can enhance their safety and reliability during storage and use. Sixth is their potential for high density. Although interstitial hydrates may have lower gravimetric capacity if compared to complex hydrates, they can still provide a favorable volumetric density, making them suitable for certain applications where space is limited. Go on to the complex metahydrates we introduced with some examples. They include ternary and quaternary compounds that exhibit superior gravimetric density compared to simpler metal hydrates. In a very simple way, let me just add this brief note. When we talk about gravimetric density for metal hydrates, we are referring to the possibility to store a larger quantity in terms of mass of hydrogen. This category encompasses several noteworthy materials like alanates, and we can see here in blue a prominent example of the so-called sodium alanate. Then these alanate have desorption temperature ranging from 200 to 400 degrees Celsius, with a hydrogen storage capacity of 3.7% by weight. Then we have the boron hydrides, which represent another significant group. This group might be represented by the lithium boron hydride, signed here with this chemical reaction. This compound offers desorption temperatures between 250 and 650 degrees Celsius, achieving over 10% by weight of stored hydrogen. As I was saying before, this is a straightforward example of gravimetric capacity. Then finally, we find the imides and amides hydrides. A prominent example is given by the lithium nitride, which can undergo the following transformations, as you see in blue. This material has desorption temperature of approximately 300 degrees Celsius and a hydrogen storage capacity of 9% by weight. Complex metal hydrides are often preferred over simple and interstitial hydrides for several key reasons. As I said now many other times, the higher gravimetric capacity, such as alanates and borohydrates, tend to offer this very higher hydrogen storage capacity per unit weight. And this is particularly important for applications where weight is a critical factor, such as in hydrogen fuel vehicles. Then they have an absorption temperature that can be much lower than other if compared to interstitial and simple hydrides, making them easier to use under normal environmental conditions and reducing the energy consumption needed for heating. Another factor is their stability and safety. The complex hydrides often exhibit greater thermal and chemical stability, reducing de facto the risk of decomposition or unwanted reactions during the storage and release of hydrogen. Then we have the versatility of these materials. They can be formulated to meet specific application requirements, allowing for customization based on storage needs and operational conditions. And then we find the reversible reactions. Many complex hydrides demonstrate more easily reversible desorption reactions, making them more efficient for repeated hydrogen loading and unloading cycles. In summary, we could say that the combination of superior capacity, better absorption conditions, stability, safety, and versatility makes these complex metal hydrides a favorable choice for hydrogen storage in many applications. Here is just a very quick slide to show you from a table of the Department of Energy of the United States, the targets of the onboard hydrogen storage for light-duty vehicle. Apart from durability and operability characteristics and charging and discharging rate characteristics, which are basically the same throughout the feature, as you can see, the main goals to reach ultimately are a higher gravimetric capacity in terms of percentage of weight, as we've seen for complex hydrides, higher volumetric capacity in terms of grams per liter, and a lower cost. So these three factors are basically foreseen as improvable into the future. In this slide, very briefly, we present an overview of the capacity of metal hydrides to serve as effective hydrogen storage solutions for fuel cell vehicles. We were saying before that one of the main application of this storage system is, in fact, the fuel cell vehicles. This slide highlights basically the properties of the major classes of hydrogen storage materials, emphasizing the technical challenging associated with each. We distinguish in three color-coded system. Red indicates that significant challenges remain in achieving the goals, the targets of these materials, and it suggests a deeply need for further research and development. Green means satisfactory performance, indicating that the materials in this category meet already the current standards for hydrogen storage effectively, and yellow indicates that while performance is adequate, some improvements are necessary to enhance the practically for fuel cell applications. Additionally, the transient reactions enthalpies below in the graph presented are intended to provide a general perspective of the entire class of materials. It is important to note that expectations may exist for individual materials that do not conform to the general trends. We can also differentiate between reversibility and thermodynamic attributes from a practical onboard perspective. Reversibility refers to the capacity of each material class to facilitate onboard hydrogen absorption and desorption. Meanwhile, thermodynamics dictates the feasibility of the theoretical operating temperature and pressure conditions for effective hydrogen charging and discharging. This comprehensive overview underscores the ongoing developments in metal hydride technology and their potential to meet the demands of fuel cell vehicles, while also identifying areas where further advancements are necessary. Um, we can easily see that in terms of the three major targets of the previous slides, the complex hydrides, as expected, do meet the requirements. Basically, they are green throughout all their um, characteristics and trends. So, very briefly, we are almost arrived at the end. We will see the advances and future technologies. In this field, we have the so-called proton flow battery, the metal hydride carbon compounds, and the nano-confinement of light metal hydrides. The so-called proton flow battery is an innovative energy storage technology that combines composite metal hydride with a reversible proton exchange membrane. One of the key advantages of this system is its energy efficiency, which approaches that of a conventional lithium-ion batteries. However, the proton flow battery distinguishes itself by offering a hydrogen storage capacity of approximately 0.6% by weight. This capacity translates to significantly more energy per unit mass compared to traditionally battery technology, positioning it as a promising alternative for energy storage application. A notable feature of the proton flow battery is its ability to eliminate the need for a hydrogen gas intermediate. This simplifies the overall system design and enhances operational safety as it reduces the complexities associated with handling gaseous hydrogen. By integrating hydrogen storage and proton exchange processes, this technology can potentially streamline energy conversion and storage, making it an attractive option for various applications. Um, for the metal hydrocarbon compounds, we can emphasize the structural characteristics and implications dedicated to hydrogen storage. Typical metal hydrides consist of a lattice, as we've seen, formed by metal ions that create ionic bonds with hydrogen. However, complex metal hydrides introduce additional compounds, resulting in hydrogen forming covalent bonds with molecular ions that contain the hydride. This unique bonding interaction allows for enhanced properties and storage capabilities. We've seen already some of these, but basically, this slide stresses the fact that under the family of complex hydrides, we can create even more complex hydride carbon compounds. Next, yes, we have A recent study by Lin et al., which explore the ways to improve the performance of complex hydrates, utilizing co-carbon catalysts. This co-carbon mixture has proven to be an effective catalyst for dehydrogenation of metal hydrates. The key mechanisms at play include hydrogen spillover, nano-confinement, and metal-catalyzed hydrogen dissociation and recombination. We could say, summing up these two slides about a derivation of the complex hydrates, that while metal hydrate compounds offer promising advantages in terms of storage capacity, further research is required to improve the kinetics of hydrogen release. And ongoing research into catalytic enhancement will be crucial for improving their viability in practical hydrogen storage systems. Lastly, this slide focuses on the concept of nano-confinement in light metal hydrates, highlighting research conducted by Young and et al. That explores basically the applications of nano-sizing and scaffolding these materials. Reducing the size of light metal hydrate compounds to the nanometer range significantly enhances their performance in hydrogen storage. Specifically, this reduction facilitates much faster hydrogen adsorption and desorption processes. The increased surface area and unique properties associated with nanostructuring play a crucial role in achieving this improved kinetics. The relatively rapid reversibility of hydrogen uptake and release in these materials can be attributed to the nano-confinement of metal hydrate compounds within a metal organic scaffold. This scaffolding not only stabilizes the metal hydrates, but also enhances their accessibility to hydrogen molecules, thereby promoting efficient storage and release. Overall, we could say that the investigation into nano-confinement light metal hydrates represents a promising avenue for advancing hydrogen storage technology. By harnessing the advantages of nanosizing, we may overcome some of the limitations associated with traditional metal hydrates, paving the way for more effective and responsive hydrogen storage solutions. This is a very brief slide dedicated to, we could say, partially the references I used for this lecture. I thank you very much all for your attention and hope that this lecture was of your like. Thank you.